Hey everyone, I thought I'd make this video to discuss how space warfare might work in the far future. Specifically, I'll discuss three weapons that combat spacecraft might use: mass drivers, lasers, and missiles. Now, lasers are a common go-to for science fiction writers, and at first they may seem ideal. They hit with pinpoint accuracy, at least at close ranges, and travel at the speed of light. However, there are some downsides. It can take a long time for them to inflict critical damage to an enemy spacecraft, all the while the opposing spacecraft could dish out damage with other more powerful weapons. A more likely use for lasers would be in a point defense role, which will be discussed later in the video. One weapon that can deliver a lot of damage at once is a mass driver, also known as a coil gun or Gauss cannon. This is one of two types of electromagnetic weapons, the other being the railgun. When electricity flows through a wire, it results in a magnetic field with lines going around the wire. Magnetic field lines exert a force on a charged particle that's perpendicular to the magnetic field lines and the particle's direction of motion. A railgun has two conductive rails, with the projectile completing the circuit. As the electricity flows through the projectile, the magnetic fields generated by the wires push the electrons in the projectile, along with the projectile itself, toward the muzzle. Meanwhile, coil guns have the wires arranged in coils, and when electricity flows through them, it forms a series of magnetic field lines which closely resemble a magnet. This magnetic field will pull a projectile that is either made of magnetically permeable materials or is an electromagnet with a coil itself. Usually, coil guns will have multiple coils, and after the projectile is pulled close to the first coil, electricity will stop flowing through it and instead go through the next coil to keep accelerating the projectile. This is repeated until the projectile is close to the muzzle at the desired velocity. Railguns are more energy efficient, but they have a muzzle velocity limit at Mach 7.5. This is because the round has to contact the conductive rails for the electricity to flow through it and complete the circuit, and this generates tremendous frictional heating at hypersonic speeds. This heat can alter the arrangement of atoms in the rails, thus compromising their ability to conduct electricity. Meanwhile, in a coil gun that would be used here on Earth, the projectile would only have to be in contact with the metal on the inside of the barrel. This will also result in frictional heating, but remember, the interior of the barrel doesn't have to conduct electricity, and usually metals will start to lose their conductivity when heated before they start to melt. However, as you increase the muzzle velocity, eventually you'll get to a point where frictional heating deforms the barrel and the weapon will no longer work. This can be circumvented if you have the projectile in an internal maglev rail so it never comes into contact with the barrel and frictional heating is no longer a problem. In space, i.e. a free-fall environment, you could omit the barrel entirely and have the round go through the center of the coils without touching them, so there would be no frictional heating. Now, when we often look at space battleship designs in sci-fi, many have their main weapons in turrets, like battleships on Earth. But whenever you decide whether or not to give a combat vehicle a turret, you have to consider a trade-off between flexibility and firepower. Here is the Wehrmacht's Panzer III. It has a 50mm cannon. This is the Sturmgeschütz III, or Stug, an assault gun built on the chassis of the Panzer III. The Stug is equipped with a 75mm cannon, and the reason it can have a larger gun is because it's built into the frame of the vehicle versus in a turret. So, while the Panzer III has more flexibility thanks to the turret, it came at the cost of firepower. Now, would combat spacecraft go for flexibility or firepower? Well, one common misconception about spacecraft is that rockets aren't arrows. While a ship will either be traveling forward or backward relative to its orientation, with a slight offset during turns, a spacecraft can have any orientation relative to its direction of motion. Since a warship has to point its bow in whatever direction it's going, it needs turrets to engage enemy ships from any direction. Since a spacecraft could point its nose in any direction while moving in a straight line, it would have little need for the added flexibility of a turret. So, the designers of a combat spacecraft would more likely opt for more firepower by having a coil gun built into the frame of the ship. Although, I should note that a spacecraft could still benefit from having turrets in some situations. While the spacecraft can point its nose in any direction relative to its axis of motion, it can only accelerate in the direction its nose is pointed. So, having some guns on turrets would allow it to engage targets that it couldn't otherwise when changing direction. What I think the most practical gun layout would be is a single main gun built into the frame of the ship with two turrets mounted on opposite sides of the craft. Apart from being used on combat spacecraft, electromagnetic weapons, both railguns and coil guns, could be used by planetary defense forces. If an opposing faction was attempting to invade the planet from outer space, surface railguns and coil guns could provide a serious problem for combat spacecraft in low orbit. The minimum altitude something can orbit around the Earth is 160 kilometers high. The formula for how far an accelerating object will travel is v squared equals 2as. The acceleration due to gravity is 9.8 meters per second squared, and Mach 1 is 343 meters per second. This means that a railgun round fired straight up at Mach 6 could hit something up to 216 kilometers high, i.e., it can shoot down a satellite in low Earth orbit, although this is without accounting for air resistance. When discharged at Mach 7.5, the theoretical maximum speed of a railgun, it will go up to 338 kilometers high. If a coil gun was fired at Mach 10, it could hit something up to 600 kilometers high, and at Mach 12.9, it could go up to 1000 kilometers high. These represent the minimum and maximum altitudes of the thermopause respectively. Now, you could argue that the invading spacecraft could fire coil gun rounds at the electromagnetic guns on the planet's surface to knock them out, but one way around this would be to put the rail and coil guns on tanks. If a combat spacecraft was approaching a planet to commence an invasion, it could fire large and relatively low velocity rounds before it got to orbit, and the gravity of the planet would accelerate the round toward any fixed weapon emplacements on the surface it was targeting. Meanwhile, the surface gun's rounds would be fighting gravity, and thus couldn't shoot back at the spacecraft at this point. Meanwhile, if the weapon was mounted on a vehicle, it would be impossible to hit from beyond orbit. The tank could simply hide in a bunker until the enemy spacecraft was close to being overhead. Now, you might ask how much damage could a round fired by a tank do to a warship-sized spacecraft, especially since it will have been slowed down a lot by gravity once it gets to orbital altitude. Well, even if the round reaches its apex altitude and isn't moving relative to the planet's surface, orbital velocity around the Earth is Mach 23.2, or 7,992 meters per second. An M829 APF SDS round, that which is used by the Abrams tank, has a penetrator mass of 4.6 kilos. If the round fired by the future tank had the same mass as the M829, it would hit an orbiting spacecraft with 147 megajoules of energy. The Iowa-class battleship's main guns fire a round with a mass of 1,225 kilos at 762 meters per second. This gives it a kinetic energy of 356 megajoules. This means the round fired by the future tank would hit the combat spacecraft with a kinetic energy roughly 40% that of a battleship shell. Not as strong, but still in the same ballpark and a serious threat. The combat spacecraft themselves would likely have two kinds of rounds: orbit to surface and interspace. The orbit to surface ones would be aerodynamically designed, like flechettes, and launched at less than 1000 meters per second from the spacecraft. Remember that since the spacecraft is moving almost 8 kilometers per second relative to the surface of an Earth-sized planet, this will give the round enough velocity to deliver a devastating impact. The other munition type would be a low-mass, high-velocity round to engage other combat spacecraft. Although it may not use single rounds, i.e. solid objects, and instead fire many small marble to sand-sized metal projectiles. This is because a single metal object could end up going right through an enemy spacecraft, depositing only a small fraction of its kinetic energy in it and minimizing any damage. Meanwhile, many small projectiles will have a larger total area over which the kinetic energy is spread over the enemy craft. You could think of it like a giant space shotgun, whose pellets don't spread out as they fly away from the muzzle. Although the coil gun could have a magnetic choke at the muzzle, which would cause the pellets to spread out if the enemy craft was at a range where it could dodge them, ensuring that at least some of the projectiles hit. Coil guns would provide combat spacecraft with an uninterceptable means by which to engage enemy spacecraft, but the rounds couldn't track a target, so beyond a certain range, an enemy spacecraft could simply dodge the rounds. This is where the third variety of space weapon we'll discuss, missiles, comes in handy. While no one can tell what the future will bring, most aerospace engineers think that if we ever come to the point where we have battleship-sized combat spacecraft, most of their engines will be powered by a fusion reactor. Now, does this mean that space missiles will have a similar drive? Well, when designing a rocket engine, a trade-off has to be considered between the maximum possible change in velocity, or delta V, and acceleration. This is because the thrust of the propellant will be the product of its exhaust velocity and mass used per second, while the power output of the engine will be the exhaust velocity squared multiplied by the mass used per second times 1/2. So, while higher enthalpy fuels like nuclear fusion can ultimately get you up to greater speeds, they can't provide the same kind of thrust that low enthalpy fuels like chemical-based ones can without melting the engine. If you want a more detailed description of this principle, you can see my video, Does a Greater Exhaust Velocity Really Make a Rocket More Efficient? Now, one thing to note about space warfare is that it won't be like it's depicted in Star Wars, and that ships aren't going to be engaging each other with broadside barrages. They'll be fighting way beyond visual range, at hundreds or thousands of kilometers away from one another. Enemy fleets would likely maneuver over the course of many weeks for a good pass at each other, and once they're in position, they'll launch volleys of missiles. If we plot their motion on a grid square, where each tick on a line is a time interval, the ships could alter their direction quite a bit, but they would do so very slowly. Meanwhile, if the missiles had a low enthalpy fuel, like a chemical-based one, they could change their direction at a greater rate, or arc more tightly, and move to intercept the enemy fleet. It's for this reason I'd argue that when/if space warfare really becomes a thing, combat spacecraft will use chemical-based missiles for ship-to-ship combat. Also, a chemical rocket motor is going to be a lot cheaper than a nuclear one. Defending against the missiles is where lasers would come in handy. While a combat spacecraft would only have a few, if any, coil gun turrets, it would still have many lasers to act as point defense weapons to protect it from missiles. You might think that lasers might make missiles obsolete by then. After all, we have prototype lasers which can shoot down missiles today, and in space, there is no atmospheric medium to attenuate the beam. But this is a double-edged sword, because on Earth, if you shoot down a missile coming at you, the fragments fall to the surface far from your location. However, if you do the same in space, you now have a cloud of shrapnel coming at you. Remember that an object moving at 3 kilometers per second has a kinetic energy equal to its own mass in TNT, and combat spacecraft may very well have closing velocities 100 times greater, i.e., 1,000 times the kinetic energy per mass unit. At these velocities, coin-sized pieces of shrapnel will hit with the kinetic punch of heavy artillery shells. Many have argued that missiles used for ship-to-ship combat in space wouldn't have a warhead or any kind of explosive charge because it would be a drop in the bucket compared to how much damage the kinetic energy would cause. I would actually argue that they would have a charge, but not one that detonates on impact, and instead one that goes off shortly before to spray the enemy spacecraft with shrapnel. Remember that if the missile hit as a solid object, it could very well overpenetrate and deposit only a fraction of the kinetic energy in the enemy spacecraft. Of course, once you destroy the missile, the fragments will no longer track and you might be able to dodge the debris field, or it could have spread out so far that by the time it hits you, the damage is minimal. To us, lasers might seem like a straight beam when compared to a flashlight, but they do spread out with distance. In a vacuum, a laser with a wavelength of 500 nanometers, that which is in the green light range, will have a spread of 160 microradians. In Earth's atmosphere, where diffraction is an issue, most lasers have a spread between 1 and 2 milliradians, which means a similarly powered laser would have 10 times the effective range that Earth-based ones would have. The iron beam can shoot down missiles up to 7 kilometers away, so a similarly powered laser used in a point defense role by a combat spacecraft could blow up a missile 70 kilometers away. If the combat spacecraft was moving 100 kilometers per second relative to the missile, the time to impact would be 0.7 seconds, not enough time to get out of the way of the debris field. However, the individual pieces would have spread out by the time of impact. Shrapnel will usually travel away from an explosion at 100 meters per second, so the cloud would have a diameter of 1.4 meters by the time of impact. If the missile had a mass of 1 ton, it would have the kinetic energy of 5 terajoules, or 1/13 the energy released by the bomb which destroyed Hiroshima. So, getting hit by the debris cloud would be like being 1.26 kilometers from the aforementioned bomb going off. I'd say it's possible for a combat spacecraft to survive such a hit, but it would incur serious damage, especially if it was hit by a larger piece of debris. Now, let's say that the missile and the ship are closing at 200 kilometers per second. The laser would be able to blow up the missile from the same distance, i.e. 70 kilometers, but because the closing speed is faster, the cloud will hit in half the time and thus spread out over half the distance. Since the radius of the cloud is halved, the surface area of the cross-section will be 1/4. Also, since the relative velocity is double, the kinetic energy will be 4 times greater. 4 times the energy over 1/4 the area comes out to 16 times the damage. Or, to put it another way, it would be like being 315 meters away from the Hiroshima bomb going off. Basically, the faster the closing speed of the missile and the craft, the less effective lasers will be for defense. If you want them to be of use in this role, they will have to be more powerful and have a greater range than modern Earth-based ones. Also, there is a rough amount of time a laser will take to blow up a missile, such as 1 every 15 seconds. But an enemy fleet isn't going to just launch a single missile every 15 seconds. They'll launch volleys to try to overwhelm your defenses. You might be able to destroy 2 or 3 of the missiles, but some will get through. When/if space warfare becomes a thing, there could be 2 kinds of missiles: tactical or ship-to-ship, and strategic or planet-to-planet. Unlike the tactical missiles, the strategic missiles would have to focus more on delta V as opposed to acceleration, and thus would be more likely to have a fusion engine to get to its target. It's often said that there's no such thing as an unarmed spaceship, because any one of them can be repurposed as a kinetic kill weapon. But in my opinion, there will be very few spaceships repurposed as kinetic missiles on a regular basis. In modern warfare, both cruise missiles and drones use jet engines, but drones are seldom repurposed as cruise missiles, and when they are, it's usually an older model that was nearing the end of its service life. This is because there's a difference between making an engine that can make something fly and making an engine that can do repeat flights, i.e., the engine on the drone will be made to last, while the one on the cruise missile won't. This means making the reusable engine will require much more precision and thus be more labor intensive. Not to mention, you also have to make it accessible for maintenance purposes. Similarly, fusion engines on a spacecraft will have to contain plasma heated to millions of degrees, and making multi-use ones will require much more time and resources than single-use ones. As such, the ones used on strategic missiles would be more crude, relatively speaking, than the ones used on manned spacecraft. The strategic missiles would act as a future ICBM, and as they approach a planetary body, they could also deploy a swarm of tactical missiles to hit specific targets near the surface, while the remainder of the strategic missile, basically the engine and the empty fuel tanks, hits the largest installation on the planetary body. Because it doesn't have to carry any fuel to slow down upon arrival, the strategic missile could fly twice the maximum speed of the combat spacecraft. If it had a mass of 130 tons and was coming at a target at 100 kilometers per second, it would hit with a kinetic energy of 65 petajoules, i.e., equal to the Castle Bravo nuke, the most powerful device ever detonated by the United States. Often, when we think of space warfare, we have a knee-jerk reaction to compare it to naval warfare. But space is not an ocean, and should it ever manifest in the future, space warfare will be unlike anything before in the history of warfare. If you truly want to get an accurate idea of how it'll work, you have to think from the ground up. And by ground, I mean that laid out by Newton, because in the battlefield of space, kinetic energy will dominate. Well, that's all I have to say on the topic, but as always, if you have something to add or an alternative opinion, I look forward to reading your comments. Thanks.